Hello everyone, we're getting started with the next test 3's worth of material starting in 3.2. 3.2 is primarily two incredibly important theorems that are supporting for the rest of the chapter. So I will be combining 3.2 and 3.3's homework assignments because it's really there in 3.3 where they start to demonstrate their usefulness. So we know that from 3.1, the extreme value theorem states that a continuous function on interval AB must have both a minimum and a maximum on the interval, but we had to plug in the endpoints to check. Rolle's theorem particularly gives conditions that guarantee the existence of the extreme value interior to the endpoints of the function, and that says let f be continuous on the closed interval AB and differentiable on the interval AB without the endpoints. If f of A equals f of B, then there's at least one number C such that f prime of C equals 0. Basically, what they're saying is that if the y value of these two functions are the same, the only way to get from point A to point B is either the straight horizontal line, where technically everything would have a derivative of 0, or for it to go up, turn around, and go back down. But if it turns around, remember those turning points really have horizontal tangent lines, which means their slope is 0 at the point. Conversely, you could go down then up, but again, at that low point, it would be the same. Now, we can look at these two pictures on the right. The first picture is something that is both continuous on the interval and differentiable on the inside. And we can see that it has a very nice point, which is a maximum, where its derivative must be 0. If you took out differentiability as a requirement, what you could have is these awkward spikes, which technically have vertical tangent lines, undefined slopes, so it wouldn't guarantee that there's a place where your derivative is 0. One way Rolle's theorem can be demonstrated is through some algebra work. For example, we know that on polynomials, very often we try to find the zeros. And so one thing that happens, for example, and this kind of looks like a piece of a polynomial, is between zeros, there's always a turning point, because if you're increasing or decreasing at a 0 on one side or the other, you have to turn around to get back to the next 0. So we can kind of use algebra to demonstrate how Rolle's theorem should work. So first, let's find the roots of the function f of x equals x squared minus 3x plus 2, and then demonstrate Rolle's theorem by finding the derivative of the function, setting it equal to 0 to show that there's a horizontal tangent line at some point between our two roots that we found. So to find the roots here, we can factor. So we have f of x equals x squared minus 3x plus 2. We're looking for two numbers that multiply to 2 that add to negative 3. So it should be x minus 2 and x minus 1, which means we have zeros of x equals 2 and x equals 1. That means that there should be a point in between 1 and 2, an x value between 1 and 2, where the derivative is 0. So let's check our derivative of our function. The derivative of x squared minus 3x plus 2 is 2x minus 3. And if we set that equal to 0, we get 0 equals 2x minus 3. Add the 3 over, equals 2x. Divide by 2, and we'll get, I'll move x to the left, x equals 3 halves. So it does demonstrate that Rolle's theorem works. We had our zeros of 1 and 2, and we precisely had the point where the derivative is 0. It happens to be 1.5 between these 2 points in particular. Now, Rolle's theorem kind of serves as a useful role, but becomes really more important for proving the mean value theorem, which is a very, very important theorem in calculus. Mean value theorem has some applications in the real world. The way it was explained to me, though, is not necessarily one that I encounter often. But so again, the consequence of Rolle's theorem is something called the mean value theorem, and it says if f is continuous on the closed interval AB and differentiable everywhere but the endpoints, there exists a number such that the derivative at that number is exactly equal to f of b minus f of a over b minus a, which is the average slope between points A and B. They're basically saying that at some point between these two, you have to hit the exact average slope of these two functions. Now, the way I imagine or think about that is that remember that slope represents kind of in some ways velocity. So I like to think of the mean value theorem as when you're driving home or driving somewhere. If I average going 60 miles per hour on my way home, my average speed, at some point along the journey, I had to be going exactly 60 miles an hour. Now, why would that be true? One of the two things would have to happen if I averaged 60 miles per hour on my way home. I either was going 60 the whole time, which definitely means I was going 60 at one point, or if I wasn't going 60 the whole time, that means my speed was moving around. But if in order for my speed to average to 60, that means I would either be going 60 the whole time or have some speeds slower than 60 and some speeds greater than 60. And the only way to have speeds slower than 60 and greater than 60 on my way home was to be at some point to cross from either the slower speed to the higher speed or vice versa, which means I had to be going 60 at maybe even for just a moment. At some point, I had to be going exactly 60 miles per hour.